Hi everyone, I'm Harshit, and I'll be presenting our work, a ranking game for imitation learning. We begin with an overview of our work. In this work, we present a rank game, a new framework for imitation learning that allows us to combine learning from preferences and demonstrations. This framework treats imitation as a ranking game for which we propose a principled ranking loss. Finally, we demonstrate that our proposed method outperforms state-of-the-art imitation methods in several simulated environments and can solve complex dexterous manipulation tasks that none of the prior methods could solve. Classical IRL methods provide no way to incorporate preferences among suboptimal trajectories. Preferences are important because they can be easy to collect and also give more information about the reward function than that is available from the expert demonstrations. Classical imitation methods rely on using gradient descent-ascent to solve the zero-sum game. This strategy often suffers from training instabilities and often is sample inefficient. Prior work in learning from preferences require ranked trajectories and work in an offline manner. Given only expert samples, they cannot recover the expert behavior. Other methods that combine learning from preferences and demonstrations either consider a restricted reward class or work in an active query framework. We present a new framework for imitation learning in the form of a ranking game. We cast imitation as a general sum game between two players, the policy player and the reward player. The reward player takes in a dataset of pairwise rankings between behaviors and learns a reward function that satisfies those pairwise rankings. A behavior is specified by a state action or a state-only visitation distribution. The policy player learns to maximize the reward function. Rank game is specified by three components. First, we consider a dataset of pairwise rankings. Second component is the ranking loss, which specifies an optimization objective the reward function uses to satisfy the behavior rankings. And lastly, we need to specify an optimization strategy that the two players, the policy and the reward, will use to solve the two-player game. Our meta-algorithm for online imitation learning performs three simple steps. First, the current policy collects empirical visitation data. A pairwise preference is established between the current policy's visitation and the expert visitation and is added to the preference dataset. Then we learn a reward function that satisfies these dataset preferences, and finally we optimize the policy on the reward function. We show in this paper that a large number of prior imitation learning algorithms can be specified as an instantiation of this game. For example, the classical imitation learning learns a reward function that maximizes the performance gap between the expert and the agent. Thus at convergence, the reward function will satisfy the ranking, such that the expert behavior has a higher expected reward than the current agent behavior. We call this form of ranking loss as the supremum loss. To learn a reward function that satisfies the behavior rankings, we propose LK, a new ranking loss. LK attempts to induce a performance gap of K between each specified pairwise preferences in the dataset. The ranking loss function provides us with a reward function that is bounded with the user-specified scale K. Reward scale can have a significant effect for learning efficiency in deep reinforcement learning, as has been found by prior methods. Second, we also show that when the two-player rank game reaches equilibrium using this ranking loss, the agent visitation obtained is close in F divergence to the expert visitation, in a bound that depends linearly on policy optimization error and the reward generalization error. Finally, at each iteration of rank game, the policy update under a reward function that is optimized using the ranking loss will minimize the divergence with the expert visitation distribution. We consider three sources of ranking in this work. The first source is generated as part of the online learning process of the agent, where we prefer the expert's behavior over the current agent's behavior. We call them vanilla rankings. The second source of rankings are generated automatically by using convex combination of existing trajectories in the dataset. This is a form of data augmentation and is also equivalent to the mix-up regularization in trajectory space. Offline annotated rankings form the third source, and they are provided by humans or from existing offline datasets. To solve the two-player general sum game, we view rank game in a Stackelberg formulation. In a Stackelberg game, two players set out to optimize their objectives, which are function of both the player's parameters. Each player also has the knowledge of other player's objective. Stackelberg formulation sets one of the players as the leader and other as the follower. In the equation below, A is the leader and updates slowly, where P is the follower and updates fast. Depending on which player, policy or the reward is said to be the leader, we get two algorithms that we refer to as PAL, policy as leader, or RAL, reward as leader. Our results in learning from observations of the LFO setting indicate that rank game achieves superior sample efficiency compared to state-of-the-art methods like Opolo or IQLearn. Similar results are obtained for the learning for demonstration setting and can be found in our paper. Rank game also achieves a higher asymptotic performance with low variance compared to previous methods. LFO presents an additional exploration challenge as the expert actions are unavailable. This problem is reflected in high action dimensional environments where no prior LFO method manages to imitate successfully. Rank game is able to solve these tasks using a handful of preferences. We also point out the complementary benefits of PAL and RAL in non-stationary imitation learning settings. First, we consider a setting where the expert agent changes its intention during the agent learning process. Here, the hopper expert decides to work backwards rather than the front. In this setting, PL adapts faster because of the fast reward update. Second, we consider a setting where the dynamics of the environments are changed during the agent learning. Here, the mass of the hopper agent is increased by a factor of 1.2. In this setting, RL adapts faster due to its fast policy update. In summary, we have proposed a new framework for imitation learning that unifies learning from demonstrations and preferences using a ranking game. We instantiate a ranking game using a principled ranking loss that allows us to obtain bounded performance gap with the expert. Our thorough empirical analysis demonstrates the benefit of rank game in online imitation learning with preferences, and non-stationary imitation settings. Thank you.